And also we're sorting them in a, basically natural order, descending order, not opposite order or descending order. So that's also something that, this focus of all the sorting algorithms is. So the first sorting algorithm that we're going to review, and so we also can see the code for it, is called selection sort. So are you guys familiar with selection sort? Like, I want you to take a moment and think about what was the selection sort. I'm going to bring the animation for the selection sort. So the book has some animations for some of these algorithms, and that's actually a good way to kind of like illustrate looking at them and see how these algorithms are working. So if I can find they change a lot in their website, so I guess I find it. So hopefully by now you are, sorry. Okay, I find it. I'm sorry. So the first algorithm is selection sort, right? So we're gonna see the animation of it and also the definition of it. So the selection sort algorithm, as you can see, it's kind of obvious from the code itself. We are going to go over the list, and it has two nested loops, right? So just imagine you're going to have two nested loops. Both of these nested loops are starting from 0 all the way to the length, and then the other one is just one element ahead, and it's still going to go all the way to the length, and that one's going to go to length -1. This one's going to go all the length. So that means we really have a nested loops, and each loop is going to go over, and that's definitely going to be in a square, right? So it's already obvious from the just looking at the code and the way the code is written that this algorithm is definitely going to go order in a square. So it's going to be considered as a slow algorithm for us, like to do. Linear is a good good enough, and we want to do as fast as we can. But see, what is the strategy behind these algorithms? As you can see, it's search. It's going to find the very first one, and it's considered that as minimum. And then it's going to start comparing that with all the other elements in the list and see if there is any other that is smaller than this one. So if it finds that, then it's going to copy the index of it. So we're going to have the index of it too. We know that it's basically, we find another one that's actually smaller than this one. And then when we're done with all this comparison, it's now basically going to find a minimum index, and then it's going to do the swapping. So you have to keep doing this, and again, and a score time for every single element. So that's going to be expensive. So it's kind of like, let's look at the animation. So basically, we're going to, this is our random list generated. So we're going to just go over the steps. But first element is going to be in the very first loop. It's going to be 31. And this is going to compare that element. So we have like J here starting from 67. So it's going to compare that 31 with 67, 31 with 79, 31, 72, and all the way to 14. And then it's going to, whenever it finds something that is, it's basically smaller, is going to do this, the bookkeeping for it, right? So it's going to come up with the for it. So the 20 is smaller than 31. So it's going to keep that index. And then immediately when we go to the next one, it's going to find a 14. So that's going to be the minimum. So it's going to go all the way anyways. And then when we're done with the first round, 14 is going to be the smallest index that we find. So that we are in the swapping scenario. So that's going to be this part of the code, right? So, oh, I'm so sorry. I guess I forgot to. Uh, yes, okay, I'll see if I can. Oh, no, that didn't work. Oh, I have more here. Is that this one? Let's see. Okay, perfect. I'm so sorry. So, um, I'm just going to refresh this because it's so let's just start from the beginning. So our sorting algorithm, it's going to start, and when it starts, is going to start comparing the very first one, which is here 62, to all the other elements. So it started from 1981, so it's going to keep going, and as it goes, it's going to kind of bookkeeping the smaller index. So 19 is the smaller, so first is going to keep the index number 1, and then it's keep going, and it find that that's 12 is even smaller than the 19, so it's going to keep track of that index, and it's keep going and say, oh, 10 is actually smaller than that, and then it's keep going. So basically it's going to find the smallest element in the list, and then it find that, which is the the step. When it's find that, then it's going to do the swapping, and so then it's going to the bigger loop, the outer loop is going to go one ahead, and so next one is going to compare 19 with all the elements, so it's going to still find the 12 as the smallest element, and it's going to do the swapping. Then it's going to start from next index, is going to the smallest elements, do the swapping. Then 23 is the smallest element. As you can see, as you keep going, the first half of the list, or the first part of the list, is going to be already sorted, and we just have to worry about the rest of the element. So again, since we have two loops here, it's going to take us order of and 2 to finish, or in a square to finish this algorithm. We can write this in a recursive manner as well, and that means that we have to find the smallest element, and then we have to put it in the beginning, and then we have to keep going, right? So you can write this in a recursive manner as well. So this is a recursive way to writing the same algorithm. So we have our sort method that's going to start from 0 to the length -1, and the other sort, it's going to check if the low and pass high, and low and high pass each other. It means we're comparing all the elements, and so there's nothing to compare anymore, so we need to do the swapping, and then we're basically going to call that the sort again this time with the low +1 and the value of the high, right? So because we have to keep going on the end of the list. So that's a recursive way to writing this algorithm. So sometimes writing the algorithms in a recursive way, it's going to help us sort for dynamic programming. So it has, maybe you can just basically just do half of the list on one machine, and then do the rest on some other machine. So that way, kind of like dynamically, you can work on it. Maybe I can look at me a little bit faster. So that's how the selection sort works. So I also want to use another website which is helping us to compare this algorithm, and also as I said, we're just not going to just looking at the algorithm. We also like to look into the way that they work with different types of data. So the selection sort, if I go to the selection sort and we look at the the data that we have here, so it's kind of showing the data in a way on this website. So the data shows that we have random type of data, we have nearly sorted type of data, and then we have data, and then we have the few unique. So the data on the very first set are completely random generated. Their second set, there's some of them are not sorted and not maybe just we added them later into the list that was already sorted, so they're not completely unsorted, just some of them. So they may basically is nearly sorted. The other one is sort of completely in the reversed order, and then the last one is just we have some we have a lot of duplication basically, right? So a few unique values. So the way we like to compare this algorithm is that to want to see if the algorithms that we have here are stable or not, how much space they're going to use, if they need to have extra space. Like for example, some algorithms, when you're comparing a list, you need to copy that list to another page, to another list or something. So you have to use an extra memory somewhere to keep the data. We definitely want to know how many comparisons we have to do, how many maybe swaps we have to do. Swaps is also another instruction, that can be expensive. And also we want to see if the algorithms is adaptive or not. So being stable or being adaptive. I guess you already know extra space, number of comparison, number of swaps. But the one thing we may not think about it before is being stable or being adaptive. So being adaptive, it's going to be shown by comparing it with different types of input. So if the algorithm change its behavior, if the data is a specific type of data, then that means that algorithm is an adaptive algorithm because it's changing its behavior. But if it's not changing its behavior, no matter what, it's always going to exactly do the same exact number of comparison, ignoring the fact that this, for example, list is already sorted. You don't even have to sorting this list. That's gonna ignore it, and that means it's not adaptive. No matter what, it's always going to act exactly the same. So it's kind of like showing in the example, but and this algorithm is not, the selection sort is not an adaptive algorithm. So I'm going to see that. Let's look at it. So we already discussed that this algorithm has two nested loops that both go order of n all the way to the end. So that means it's going to act as order of n2. And so you can see the order of n2 complexity in all these four. I'm going to run it again. In all these four different types of data, this algorithm is going to exactly finish at the same exact time, right? So the number of comparison, the number of the swaps are going to be exactly always the same. So it's not adaptive, right? So no matter what, it's always going to have the same performance. It's not using any extra space, and we already know the number of comparisons is the worst. Basically, the bottleneck to this algorithm. Number of swap is still in order of n, but number of comparison is the bottleneck of these algorithms, and the worst case is going to go all the way to the order of n2. So that means that's the performance of this algorithm, right? So it's not adaptive. But what is a stable means, right? So being a stable makes sense when we have these types of a few unique or lots of duplications in our input. So